Okay. So welcome everyone to optimization in civil engineering. Today we will be discussing something that I find interesting in the week one content. That is convex concave function. That is just minimum and maximum of a function, and then how to optimize the multivariate function. Okay. So before we go into the content, so here if you are wondering why this blue box is there, so the video is going to be uploaded into the YouTube channel, which we had to make according to NPTEL's regulations. And so the way I am recording is the video will come in this blue box or somewhere around the blue box. So to avoid any content being here and then being overlapped by the video, I have kept a blue box as a reminder. Now, so all of you are higher than first year, so I assume you will be knowing how to calculate eigenvalues of a vector. So I want you to give me the eigenvalues of the vector that I have shown here. So if you have any doubt in calculating eigenvalue, then maybe you can go to the YouTube channel by my name, and you can have check the week zero video. It's a dry run we had to make. So it's a 19-minute video where I talk about how to calculate eigenvalue and eigenvector. You can look at that. But for now, I think people probably know how to calculate it. So give me the eigenvalue for this particular matrix. It's an integer, so it won't be that much complicated. That much I can tell you. So later on in this course, we will be actually being introduced to some programming, R and MATLAB. There it is very easy actually to calculate the eigenvalue or eigenvector of a matrix. We'll look at that maybe. But for now, we have to be aware of how to calculate an eigenvalue of a matrix. So anyone has an answer? Okay, so let's just not wait on this for too long. If you are solving it, you can check later that whether you got the eigenvalues as 5 minus 1 or 2. So this is the answer actually. The point that I want to make with this slide is, if you know the eigenvalue of this particular vector A, can you tell me the eigenvalue of vector B, matrix B and matrix C without doing any calculation within 1 minute or within maybe even 30 seconds? So if I give you the eigenvalue of this matrix A, I want in chat, or you can unmute and tell me the eigenvalue of this matrix B and C without calculating. So for that, can anyone tell me what is the relation you see between the matrix B and A? Take your time. And yeah, and how they have been changed? You're on the right path, yes. It's the how they have been changed, if you can notice. It's a fixed change. In the B and A, I am asking. We'll come to C later. Let's talk about B and A. Okay, so the thing is, I have added 3 to the diagonal elements of A to create B. Is it visible now? Oh, okay. Yeah, so okay, I'll make it clear. So I have only done a linear operation between A on A to create B and to create C. So now that I have told that I have just added diagonally, I have added 3 to this matrix A to create B. Can anyone tell me how I have gotten C from A? Absolutely correct. So once you have identified this thing, then it is just a matter of doing the same thing to the eigenvalues to get the eigenvalue of the new matrix B and C. So if you see for B, what we did was we added 3 to the diagonal elements. Then the eigenvalue will be addition of 3 in the eigenvalue of A. So 5 plus 3 8, then minus 1 plus 3 2, and 2 plus 3 5. Similarly, what we did in case of C was we multiplied the matrix first by 2 and then we added 3 to the diagonal elements. Now the eigenvalue of the C is same. Multiply 5 by 2, then add 3. So 10 plus 3 13. Similar case, minus 2 plus 3 1, and 4 plus 3 7. So this is something that I wanted to make you aware of in this particular slide, is that if you are doing any linear operation on a matrix, then you can do the so like it won't work if you add this a scalar to the non-diagonal elements. Only the multiplication to the non-diagonal elements and scalar addition and multiplication to the diagonal elements, you can do that. So that's why I have kept here I. If you all know, I hope you know that I is actually uh, identity matrix that is having one in the diagonal and other are zero. So if you have to add any scalar you have to a matrix, then you have to multiply that scalar with the identity matrix and then add. So if you do that, if you then your eigenvalue will also be the similar linear operation. And in all the cases, okay, so in all the cases, the eigenvector actually is not going to change. So the eigenvector of A was V, set of vectors. Let's call them V. Then the eigenvector for this A plus 5 is also V, and 2A plus 5 is also V. So maybe in it can be useful for you in some of the questions, not here, maybe in some competitive exam. Okay, yeah. So now let's come to the topic for today's presentation: convex function. What is a convex function? So a function is convex if between any 2 points, let's take A and B, if between any 2 points on this function, if we go inside that and choose a point, let's say A into t plus 1 minus t into b, so t here is less than 1. When t here is less than 1, then you change the value of t from 0 to 1, you will get points inside this particular A and B. So for any 2 points A and B in this function, this particular point, the value of the function that you will get will be lower than the value of the if you do the same operation on the values of A and B. So basically it's a dome, right? If you do a linear interpolation, let's take t equal to zero point 0.5, then you will get a point which is just in the middle of A and B. And then when you go up, this will be somewhere where you will have the value of the function from the function f of A plus B. Now, if you do the same operation of fa plus fb by 2, a linear interpolation, then what the value you will get will be on the straight line. So this is what is actually convex function. When you do the linear interpolation between any 2 points, then the result of this linear interpolation, if it is above the yeah, okay, so someone, okay, Oh, no, no. Okay, so t is just. So I forgot to write here, but okay. So t is just from 0 to 1, some number. So when so x is equal to a into t plus 1 minus t into b. So if t is 0, then what is x? Yeah, Pankaj, tell me. If t is 0, then what is x? Yes, and if t is 1, then what is x? A. So t is actually can vary from 0 to 1, so that we can get a point that is between a and b. Okay, it's like a general description of if you want to write a point that varies from a to b, then you write it in this form and you mention that t can vary from 0 to 1. Okay. Yeah. So this is what a convex function is, and I like to call it a bowl shape function. That if you do an interpolation, then the point will be above that. It's like filling up water. It can hold the water. Yeah. So how do I identify if a function is convex function or not? So here's the thing. So as Rito already has told you, calculate the first derivative, second derivative for maximum minima. We also have to do the same. You calculate the first derivative, then you get put it equal to 0, and then you get the stationary point, and then you calculate the second derivative, and then you put the value of that stationary point into the second derivative. Now if that particular after putting the second derivative in the stationary point into the second derivative, if you are getting a value greater than or equal to 0, then you can call it a convex function. What does that mean? Yeah, Pankaj, please. Yes, yes, yes. Yes. Except this means slope is increasing. Yes, yes. So yeah. So the thing is, if your slope non-decreasing means slope can be the rate of increase of slope can be 0, right? If the slope is non-increasing, so let's say we have a function that increases and then becomes constant, saturate, right? If we have a function that increases and becomes constant, just 1 minute. I have to, yeah. Okay. So then we can. So that means the slope is not decreasing, but it is not increasing also. So we have to say there that slope is not decreasing. Yeah, yeah, yeah. So this is condition to include the horizontal line also in this scenario. So you can call that function f of x as convex, but when it is, but we cannot call it as strictly convex. Strictly convex means the slope has always to it has to increase. Okay. So similarly, you have okay. Okay. Yeah, similarly, you have concave function. Now it is a dome shape function, like we have in our temples, right? So it's an inverted bowl. You can also say that inverted bowl if you want to say. So if you take any point between a and b, and you calculate the value of the function at that point, then the value you will get will be higher than if you do the same operation on the value of each point. So we'll look at some points if you are not very comfortable with these things. So then we'll look at some examples, and then it will be a little bit clear. Okay. So just yeah. So the same thing as we did in the case of convex function. So you calculate the double derivative for this concave, and if it is less than or equal to 0, or that if the slope is not non-increasing, then it is concave, and if the slope is decreasing, yeah. So the difference between non-increasing and decreasing is just this 0. If it is non-increasing, you can call it as concave. If it is decreasing, then you can call it as strictly concave. So what I want you to take away from this particular two slides is that if your double derivative at any point is greater than equal to zero, you call it greater than zero. You call it as convex. If it is less than zero, then you call it as concave. Now, as also discussed by Rito, if it is zero, then we it is both in the domain of convex and concave. So in that case, what we call is actually the second derivative test has failed, and you can go for a higher derivative test, or you can go back to the first order derivative and try to do some checks. So we'll do that. So we'll do the first order. We'll not go for the higher. I like doing the first order, so I will discuss that. So let's take this example. In this example, we'll have that case. So what I want you guys to do is tell me what is the first order derivative and the stationary point for this particular function. It will be integer, I can assure you, so you can do it, I think, quickly. Yeah, Pankaj, you have something to ask? Okay, yeah, yeah. Tell me. Plus, maybe it is not clear. It is 3 actually. Yeah, yeah, yeah. Okay. Yeah, so this is how you calculate the first derivative. And wow, very good. Someone has already told the stationary points also. That is correct. 0, 1, and 2. Okay. Now let's check the nature of this particular function at x is equal to 1. So for that, what we have to do? We have to calculate the Yeah, we have to calculate the second derivative. And can anyone tell me what is the sign of the second derivative? So yeah, one more tip. Like if you want to keep it, you can keep that tip. Is that you see this is 60x power 4 minus 180x cube plus 120x square. When we are going for the third derivative, no sorry, the second derivative, we are interested in sign, not the value exactly. So you can just take common and make your life easy. So yeah, if you want to do that, you can do that. So yeah, can anyone tell me whether the second derivative at x is equal to 1 is positive or negative? Okay, I see silence. So I think it is too simple for you guys, so I will just show you. So the second derivative at x is equal to 1 is actually minus 60. So that means f double dash x. Yeah, so Prasanna has told negative correctly. So when it is negative, it is local maxima. That means the function is actually, so okay, yeah. So what is the function? Is it convex or concave? Concave. Correct. So let's go for x is equal to 2. Okay, so I didn't hide it for the first time. Okay, so when you do for x is equal to 2, you will get the sign of the double derivative as positive. That means it is convex at that side, and the function is actually local minima at that particular location. Now the comes the interesting stationary point. That is x is equal to 0. Now you see everywhere in this double derivative we have x. So when you put x is equal to 0, the value will be 0. So in that case, we say that second order differential test has failed. Now instead of going to a higher order derivative, I will go to a first order derivative test and then check. So what is this first order test? It is shown here. So let's say x is a point where your second order derivative failed. That means the func. Okay. That means first of all it was a stationary point. So the f dash x is 0 there. Then what you do is you go just a right, just a little right to the x. So let's say we add a very small value to that particular x, and then we calculate f dash x. If it is less than 0 on the right side, that means the slope of this function is decreasing on the right side. If and On the left side, if it is greater than 0, it just reduce a small number from x. That means it was increasing on the left side. So this is what it will create. So the slope is increasing, the function is increasing here and the function is decreasing here, so it will be a local maxima. And in this case, if the reverse is happening, if like the function is decreasing here and the function is increasing on the right side, then it is local minimum. Now this is what either one of these four conditions is going to happen when the second for the stationary point, right? So if we can identify the local maxima and local minima using this case, then why do we go for the second derivative? So actually, in you will see now in this example itself that sometimes it is actually not very clear that just looking at this value of the differential and just adding some arbitrary number, whether it is going to be positive or negative. So we go for the second order derivative, or sometimes we want to do it quickly, we go. Otherwise, you can do this local maxima, local minima just based on this first order derivative also. Yeah, so the remaining two cases, if your f dash x is increasing on both the left and right hand side, then it is a rising inflection. And if both f dash x is less than 0, then it is a falling inflection. So can anyone check and tell me where does our x is equal to 0 lies in all these, out of these four scenarios? Yeah, so you have to do it quickly because we have some more interesting things to discuss than this. Yes, yes, Prasanna, tell me. Rising inflection. Yes, you are correct. So, okay, so Prasanna, tell me, did you, on which side, whether the left or the right side, which side did you face a little bit of? So, how did you proceed with it? Did you choose an arbitrary value for this epsilon, or you just took epsilon itself? Sorry, you kept it epsilon. Yeah, cool. Yeah, it is correct. It is correct. Yes. 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 So yeah, so let's see here. So that's what we have to do. So I kept x is equal to 0, then x minus epsilon. When you put f this here minus epsilon, then it will be power 4, power then minus of power 3, and then square. So it's all positive. So then f dash of minus epsilon is actually greater than 0. That means the function is increasing on the left side of x is equal to 0. Now, when we put x is equal to plus epsilon, so actually Prasanna was able to get it correctly, but I had a little difficulty to determine the sign of this thing. So I just put epsilon is equal to 10 to power minus 6. And then the value that I got was sorry, so here it should be f dash of plus epsilon. So value that I got was greater than 0. So that means the function is increasing on the right side of x naught also. So it is going into this particular scenario of our first order test. So we call x is equal to 0. This function is a rising inflection. Is that clear? So if you also like me are facing some kind of problem, then in our exams calculator is already allowed, we can just do this and get this over with. Or if you are comfortable using the third order for tests, no higher order tests, then you can do that also. Okay. So what about the case of multivariable functions? So all these things that we discussed, you can do for a single variable function. But what about multivariable function? So for multivariable function, we have to actually make something called a Hessian matrix. So let's take an example, and then we'll make the Hessian. So basically, it is the matrix of the double derivative. So how I like to make this matrix, I will share with you. Yeah. So okay. So we need the okay. So yeah. So the point is we want to know whether a multivariable function is a convex of either of convex nature or concave nature. So what we do is we create the Hessian matrix, and then we find the eigenvalues of that Hessian matrix at the stationary point. So how do we do that? We'll discuss with the example. Okay. So we have this function fx is equal to x square plus y square plus 2x, and we'll create a Hessian matrix. Before that, I wonder why I have put this here. Okay, yeah. So the rules. Okay, so once you calculate the eigenvalues of this Hessian matrix, then there are some rules which will tell you that based on what eigenvalues, what is going to be the nature. So if the eigenvalues are positive, then the matrix, this Hessian matrix, is positive definite, and the function is strictly convex. If the eigenvalues, all eigenvalues actually, if all eigenvalues are negative, then the matrix is negative definite, and the function is strictly concave. If some are positive, some are negative, then it is neither strictly convex nor strictly concave. So before we proceed, I want to ask you this. Tell me, what is the relation between the multiplication of the eigenvalues and the determinant of a matrix? Yes, yes, tell me. Okay, very good. That is correct. So why I actually asked this is, so let's say you have a 3 by 3 matrix, and Hessian matrix, you get a 3 by 3 Hessian matrix, and then to identify whether that particular multivariate function is convex or concave, you have to calculate the eigenvalues. Even if it is integer, it is going to be a solution of a non-linear equation, like a third order equation in lambda. You guys know about the characteristic equation, right? How we calculate the eigenvalues of a matrix. Are you guys aware? Okay, good. Yeah, so yeah. So nah, I should have asked this question earlier actually. Yeah. So we know that we have to solve a third order or maybe second order equation in the lambda to get the values. Now, what you can do a hack, it will not work every time, is that you can calculate the determinant of that particular matrix. And if the determinant is negative, that means one of the eigenvalues is negative in the and one of the eigenvalues is positive, right? So or if the determinant is zero, then there is a zero in this particular there is one of the eigenvalues is zero. So you can just directly tell that this function is not convex or concave without calculating actually the eigenvalues. So that with that away, we will do an example. And yes, I was telling, I will tell you how I like to calculate make my Hessian matrix to avoid any confusion. So instead of writing this first order matrix of a function of a partial differential in a like a row, I will write it as a transpose. I will write it as I will write it like this. And to create the Hessian matrix, what I will do is I will take this particular first element. I will first differentiate this with x, and then again differentiate this with y, and then I will take this second element, I will differentiate with again with first with x and then differentiate it y. So it is like a step we can follow to avoid any confusion in a higher order multiple variable function, that where which value goes, right? So this maybe you can we can use now. Can you guys construct this Asian matrix for this particular? Oh, okay, Asian matrix for this particular function. Give it a shot. Let's see. Just maybe say we done, and then maybe I can go to the next slide and you can check whether it is correct or not. Yeah, correct. Prasanna has told correctly. So just we'll also do it once. So what I was trying to say here, we can just check. So the partial derivative of this thing with x is 2x plus 2, that is here, and the partial derivative of this fxy with y is 2y, that is here. So what we do is first we differentiate this particular element by x, then we get 2, and then y we get 0, we put it here, and for 2y we differentiate with x is 0 and then y it is 2. So this is how we can get the Hessian matrix. Okay, now here is another example problem. We have to determine the Hessian matrix for the function below. Yeah, so let's calculate the, so this is the first first order differential matrix that we get after differentiating partially with x1. So I actually when I see this x1 x2, I like to write x1 as x and x2 as y. If you are comfortable with x1 x2, you can do that, or you can change it to xy and go on and solve this. So this will be our first order differential, and using the same technique, now can you tell me what is the Hessian matrix? Just say done, and then we'll see. So I have a message. Oh, it was okay. Okay, so while you are doing that, I will also say we first differentiate this with respect to x1. So what we will get is 4x1, and then we differentiate with this with respect to x2. We will get minus 2, and we the second element will differentiate with respect to x1. We'll get minus 2, and again we'll differentiate this with respect to x2. We'll get 4. Yeah, so Sunna has done correctly. This will be the Hessian matrix for this particular uh, question. Now, see, in this case, we have seen the Hessian matrix has x1 in it also. So that can happen sometimes. When this happens, then either the question is actually asking, if it is given in the form of variable, then it is fine. You can write, you can choose that option. If the variable is not there, then probably what they are doing is they are determining the stationary point. What is the value of x1 and x2 for this particular f dash matrix to be 0, and then they are putting that value in this and getting the Hessian matrix. So that's what we will also do. Now we needed to know whether this function is convex or concave. What we did is we calculated the Hessian matrix, but it is in variable form. So how do we go about solving this? We go and calculate the stationary points by making this f dash matrix equal to 0. So yeah, so this is your f dash matrix. Now to make it 0, you have to put each of these element equal to 0. And now, can anyone tell me what is the value of x1 and x2? And that is the actually the stationary point. So how we can go about solving is this is we can put this 2x minus 4 on the right hand side and divide by 2. Then we get the value of 2x 2. We can just substitute it here, so it will be a quadratic in x1, and we'll get the two values for x1, and correspondingly we will get two values of x2 from that x1. So we will get two stationary points actually. Yes, anyone? No need to give me x2 also. You can just tell what is x1, and maybe we'll see what is x2. If you get x1, x2 is easy only. Yeah, so I don't think it needs to be mentioned, but it will be beneficial for you if you are solving it. See, I have a X level of understanding of a subject, and you have Y doubts. Some of those doubts are not under my X level of understanding. So if we work together, we can both reach to X plus Y level of understanding. You know, so to do that, to get there, you have to solve these questions. And if you get a doubt, you can just post it in chat or ask. Okay, so is it too difficult? Yeah, okay, very nice. Prasanna has told us the value, and it seems maybe a slight mistake. Let me check. So what you will get x1 as -1, that is correct, and corresponding x2 will be, yeah. So someone, yeah, Diksha, you have unmuted yourself. Okay, my mistake. Fine. So So you will get x1 value of -1 and 3 by 2, and corresponding to -1, x2 will be minus 3 by 2, which you can get from this particular equation, and corresponding to 3 by 2, you will get x2 of -1 by 4. Probably some slight mistake might be there in your calculation, Prasanna. You can check it, and can so these are the correct values. So what are the stationary points? There are two stationary points. One is x1, x2 -1, 3 minus 3 by 2, and one is x1, x2 3 by 2 and -1 by 4. Now we will put these values and get two Hessian matrix, and then we will check the nature of this multivariable function at each of these stationary points using the eigenvalue of the Hessian matrix. So let's do that. Let's take first point -1 minus 3 by 2. So here this function, this matrix only depended on x1. So we'll just put the value of x1 -1. So this will be the Hessian matrix, just -4, -2, -2, 4. Yeah. Now tell me the eigenvalue of this particular matrix. Come on, anyone else also? Give it a shot. I know this video will be available on YouTube, but you know, real real time experience is something that we should treasure, right? So let's see. So it is plus minus root under 20. Is that what you got, Prasanna? Okay. So now can now someone else than Prasanna. Prasanna is a sincere student. He is listening to what I am saying. So someone else than Prasanna, tell me. Oh shit! I have already I have already written here that it is neither convex or concave at minus 1 and minus 3 by 2. Yeah, so the thing is, if both the eigenvalues are positive, then the Hessian matrix at this particular point would have been a positive definite matrix, and when it is a positive definite, it is a convex. Yeah, convex at that particular point. So one is positive, one is negative, so it is neither convex nor concave. And what is it actually at that point? That we are not going to discuss. So that's out of the scope for this syllabus. We'll just leave it at that. That okay, this function doesn't have. It's not a convex or concave. Let's try another point. Different point. X is equal to 3 by 2 and minus 1 by 4. So when you put 3 by 2 into this, you will get 6, and the other elements are same. Okay. So some since Prasanna is only responding, so I will call out the name. Do you want me to do that? So let's say, can Pankaj tell me what is the eigenvalue for this Asian matrix? No need to worry, man. If it is not correct, doesn't matter. We all learn from our mistakes only. Okay, it should not take this much time. Okay, now anyone? Now the question is open to anyone. Ah, correct. So George and Prasanna also was trying to answer that. Both have calculated it, and that is correct. Is it minus 5 actually? Let me check. Maybe I have done mistakes. See, that's what I was telling. We all make mistakes and we learn from them. So is it plus 5 plus minus root under 5? Oh, so maybe George can check the. Okay, okay. No problem, no problem. So this is plus 5 plus minus root under 5. So in both the cases now, the eigenvalue is greater than 0. That means the matrix is positive definite, and it is having a local minima at the point 3 by 2 and minus 1 by 4. Okay, so now we know how to uh, identify the point of local maxima and local minima if there is one in a multivariable function. Now, how do we use that? So, how do we use this particular what we have learned here? In the in our field. So this is actually used in optimization of functions, multivariable functions. The optimization can be constrained optimization. It can be unconstrained optimization. So what does it mean by unconstrained optimization? Is that the value x and y for this particular example, it can go. It is like there is no limit. It can go anywhere, but yeah, so that's unconstrained optimization. If there is a constrained optimization, that means there will be some kind of limit, so some relation, or x has to be greater than 0, y has to be greater than 0, all these kind of things. I am sure you guys would have heard about these things. If not, then we will discuss here only in coming slides. So this is unconstrained optimization. We use what we have learned here, in this particular optimization technique. It's the same thing that we just learned. That's just identifying whether it is convex or concave, and then at what point it is convex or what point it is concave. So let's do it again. Yeah, do the partial differential and get our f dash matrix, and tell me what is the stationary point. I think it is too simple actually. It is not an integer, but it is quite easy. So from this particular, putting each of these element equal to 0 is what we will. Yes, yes, yeah, Prasanna, tell me. Correct. Yeah. So just to repeat for those of you, if you have any doubt, to make this particular vector or matrix equal to 0, we put each element equal to 0. So when we do this, we will get x is equal to y, and then we just put it and make it equal to 0. You will get x and y both as 1 by 3, 1 by 3. Now let's check the nature of this Hessian matrix. So see, again, for simplicity, I have kept here this thing itself. So how do we get the Hessian matrix? This first element, we differentiate with respect to x first, and then we differentiate, partial differentiate with respect to y, and then the second element we do here, and then with x, and then with y. So what will it be? Minus 8. Yeah, yeah. Oh, very good. Yeah, so yeah, so Prasanna has gone one step for ahead and told the eigenvalue itself. Yeah, but still, I will say how we got this Hessian matrix. So we differentiate this one with respect to x. So minus 8 with respect to y, 2. Here with respect to x, 2, and y is minus 2. So this is what you should get, and this is what I think Prasanna has gotten, because then after that, what we have to do is we have to calculate the eigenvalues, and he has gotten correct eigenvalues of minus 1, minus 5 root under 13, and minus 5 plus root under 13. So I'm not stopping here for you guys to tell me the eigenvalues, because I think it is pretty simple to calculate now. So minus root under 13 is actually somewhere around between 3 and 4, so it will not be able to make this positive. So both eigenvalues will be negative, so that means h is negative definite, and the stationary point, sorry, it's exactly strictly yeah, that's correct, correct. So yeah, I also do some this mistake actually sometimes, that I try forget that strictly convex or strictly concave. So that's just something that will come with practice. So don't worry about that so much. Yeah. So this is a maxima point for this function, because it is a negative definite, and this particular function is concave function. That is what a dome function. And what you can do is you can actually type this particular equation that we saw in Google, and it will give you the shape of this equation, which will exactly look like a dome, and then you will see that the maxima will be at this point only, 1 by 3 and 1 by 3. So that's something you can check out later. Okay, now let's come to constrained optimization. So I don't know, I don't think sir is teaching this, but uh, here's the thing. When I was introduced with this Hessian matrix, i was introduced it I was introduced with the problem of optimization. So when I see a Hessian matrix, I cannot just leave at Hessian matrix. I want to do some problems of optimization with it. So we have discussed now unconstrained optimization. Now we'll see a problem with constraint optimization, and in the next lecture probably I will with equality constraints now, and next lecture probably we'll discuss about the what's the does anyone remember the name of the inequality constraint optimization? No one. Yeah, so there's a name, Rang, Tucker. Yeah, Tucker technique or method for optimization. And for linear, it is actually simplex method that sir is the content is live on the NPTEL platform. So we'll discuss both of those things in the next class. So let's see how do we optimize this equality constraint. So yeah, real life problems, as we know, they will have some kind of constraints. Definitely, it will not be like no constraints. So let's say we take an example that we have to design a tank that has to have a volume of V, but we want to reduce the cost of painting the tank. Now, how do we? Where do we paint the tank? We paint on the surface. So what this is telling us, we have to minimize the surface area of that particular tank, but we have to keep the volume at V. So this is kind of a real life problem that we can discuss. So the variables will be the radius and the height of the tank, assuming it is a cylindrical tank, and this will be the equation for the surface area, and the constraint is this particular volume has to be maintained. Okay. Yeah, so we'll not be discussing this one. We'll discuss a simple problem to understand how do we go about doing this. Okay, so people are still joining. Maybe next time join a little bit earlier. Okay, yeah. So in this case, what we have to do is we have to slightly modify our function, the main function. So by introducing something what is called as a Lagrange multiplier. So let's say we have to maximize or minimize a function fx, where this x is actually a vector. So basically, this function f is a function of n variables, so x1, x2, x3 till n. And the constraints that we have, that is the equality constraints, are m. There are m constraints. So here we saw one function and one constraint. So there can be n functions and n constraints. So for now, for our ease, what we'll do is we'll consider only those cases where number of variables are more than number of constraints. Because if the constraints are more than the number of variables, then the problem is overdefined, and probably someone can solve it, but this that's not the under the scope of this particular syllabus. So we'll be discussing only the problems where the constraints are less than the number of variables. Okay. So when this is the case, when this is particularly you have, then you modify this your function that you have to minimize or maximize by adding these constraints to the function, and multiplying them with a lambda, which is called a Lagrange multiplier. So the first function, the first constraint we multiplied with lambda 1, the second constraint we multiplied with lambda 2. So likewise we have number of lambdas equal to the number of constraints. So now we have this particular equation L, let's call it Lagrange equation, that is fx plus lambda summation of so this is what we can write it as fx plus summation of lambda j gj from j going to 1 to m, which is simplified into this particular thing. Now, what are the variables? First thing is we don't know x1, x2, x3 till xn. So there are n variables here. And then we introduced m more variables, that is lambda 1 to lambda m. So unknowns are now n plus m. Now, how do we identify these unknowns? We follow similar step that we did in the earlier case of multivariable. That is, we treat these also lambdas also as some variables. We don't know what variables they are, but they are some variables. So what we will do is we will just calculate a stationary point that is actually going to have the value of x1, x2, xn, and then lambda 1, lambda 2, lambda n. So we partially differentiate this particular function, that is the L x lambda, by x, and we differentiate it with lambda, all the lambdas. When we differentiate these functions with x, we get n equations here. We differentiate these functions with lambdas, then we get lambdas equations here. and using those n plus m equations we can get the n plus m values for these variables. Okay, maybe I'm going over time, so we will take an example and try to get this particular derivative, and maybe in the next class I can continue. Yeah, so good evening, sir. Sir, don't know whether this question was discussed or not. Can you please? Okay, can you please explain once again? Okay. Yeah. So, see. Okay, maybe if this is a question, we can check this question out. So, Surya is asking that there is a function f of xy is equal to xy minus 3y whole square and x square minus 2y whole square, and then Hessian matrix was asked. I think same question was asked by Diksha, probably Diksha, in Ritu's class. So actually, uh, if you make the Hessian matrix, maybe it will be in the form of a variable. If it is in the form of constant, then well and good. We don't have to do anything. We just calculate the eigenvalue and uh, yeah, so we don't have to do anything. But if it is in the form of a variable, what you can try to do is calculate the inflection point. Yeah, so to calculate, okay, let me go to that particular question itself once. So here you see in this particular question, Surya, right? Yeah. So in this particular question, when you first calculate the f dash x, it will be this column vector actually, but I am writing it as a row vector f dash x, and then you differentiate it and you get the Hessian matrix, right? Now here it is in the form of variable. Now you are asking that there is no point is given, so how we will get the Hessian matrix? So in that case, I am not 100% sure. I'll ask the TA, the main TA of the designer of that question. But what I think is what you have to do is you have to calculate the stationary point. So when before calculating the Hessian matrix, you would have calculated the first derivative of this function with x and y. You put those derivative equal to 0 and get the value of x and y. Put that value into this particular formula for Hessian matrix, and what you are going to get in the end, probably that's what they are asking. You can check if the option is matching, then probably that's what they are asking. If not, then maybe the value is missing. Oh, it's somewhat difficult to identify the stationary point. Okay. Yeah, it looks also difficult. That is correct. So maybe we'll check. We'll check what's going on with this question, and we'll get back to you. Okay, Surya. Maybe you can put this question in the discussion forum also, and there some the TA can respond to this. Yeah. Okay. So where were we? We were in this. Yeah. So let's take an example. So we have. You know what? Actually, it's already 5. Yeah, and what we can do is you guys check. You guys note down this particular question. So we have to check whether this is a maxima or minima. This particular question fx, which is subjected to equality constraint gx, that is equal to this x plus y is equal to 5, and we have to, for now, just try to do this. So create a Lagrange equation. What is that equation? You just yeah, you just add this inequality, bring the 5 to this side, so x plus 5 x plus y minus 5 equal to 0, and multiply it with lambda and add it to this particular equation. So we get a Lagrange equation like this, and then we have to differentiate this particular equation with each of the variable. So we have x, we have y. Now we have introduced one more variable, that is lambda. So solving these three, actually, we will get the value of x, y, and lambda, and that will be one, maybe one or two stationary points we'll get, and then we can go ahead and identify whether it is maxima or minimum. So yeah, so I think what we have further, it's a little bit time taking, so I will probably discuss it in the next class. What you can do is you can note down these and try to get the x, y, and lambda, and we'll, so please share the PPT for further study. Yeah, yeah. With this PPT, we have to share with NPTEL, and they will share it with you. So don't worry about it. So I think this will be it for today. Is there any doubt in what we have, what I have tried to explain today till now? Hmm. So there is no doubt. Okay. So good then. Then maybe you guys have understood everything. And but I see, actually, if you have a doubt now, you can ask now, because afterwards it is going to become much interesting, much more interesting. And if you are falling behind now, then it will be a problem later on. See, all these big matrices will come. So it's, if it's better if you are clear up to now. So I will give you one more chance. Is there any doubt? Okay. Okay then. So that's it for today's session. We will discuss in the next week Sunday, same time 4 to 5, and Rito's session will be 3 to 4. You guys can attend either of the session. Yeah. Most of our contents will be same, but not necessarily everything will be same. So yeah, you can attend any of the session or both the sessions. Okay then. Thanks. We'll end the call for today.